let's talk about bugs. Not necessarily the most glamorous part of computer programming, but a very central part. So here's a quote from Maurice Wilkes, who sadly died a year or two ago, but he was based here in Cambridge. And I mean, by some very reasonable claim that he was the world's first real computer programmer. He was the first person to use a computer to solve a problem that wasn't, can I build a computer, general purpose computer. And in his memoirs, he talks this notion of realizing that a good part of the remainder of my life was going to be spent finding errors in my own programs. So the words bugs and debugging hadn't been invented at this point. Anybody who's done any programming probably is, at least if they can remember back that far, can remember that sort of sensation that you realize, writing code is really hard. And it's not just figuring out what to write, it's making it work. I mean, there are studies, famous Brooks Mythical Man Month, they found that on average, developers produce 10 working lines of code a day, and which sounds bonkers, and actually in modern languages that can be a bit higher, but it's roughly right. And the reason is, of course, you can write 50 lines of code by lunchtime on Monday, but then you spend the rest of the week making those lines of code work correctly. In fact, if you think about how much time you spend debugging, and how much of your programming time, well, if you think less than half, then you're either unusual or delusional. So studies have shown this, that people spend about half their time debugging, especially if not necessarily bugs that come from the QA department or from a customer, but maybe nobody else sees that bug. Right? You're writing code, and it didn't do what you wanted it to do, and now you have to make it do the right thing. Nobody else knows that bug exists, but it still exists. It's just a little secret. And this is a big problem on a global scale, right? So if you just take that 50% of programmers' time and you do a bit of simple arithmetic with 16 million programmers in the world, and they earn on average this, and then that's what the wage bill for all these developers just debugging stuff comes to $312 billion a year, which even in these modern times of international bailouts and the like, is still a lot of money. In fact, in the years 2008, 2012, right, the real peak of the Eurozone crisis, we spent twice as much debugging software as we did on all of the bailouts of Greece and Ireland and Portugal and Spain put together. So we spent twice as much debugging software as we did debugging the Eurozone in those years. But it's not seen as a big problem, right? It's just part of life. And to a large extent, to some extent that's true. Bugs are going to be, there are always going to be bugs, and you're always going to have to pay people to fix the bugs. But my contention is that we're suboptimal as a society, and the cost of bugs is a big, it's a significant economic drag on the global economy. But that's just the wage bill, which is the bit that's easy to calculate. So that's why we have a nice number for that. But there's this other stuff that's really not very easy to calculate, but is clearly very significant, and is pretty clearly more significant than just the wage bill, which is the delays in time to market and projects that have loads of money spent on them and then get cancelled. In the NHS IT system, very sort of famously, lots of government IT systems spent a fortune on, and ultimately they can't get the bugs out, they can't make it work, and it gets cancelled. Personally, I suspect there's nothing special about government IT projects here, other than they're just more visible. I suspect there's an awful lot of corporate, I've been involved in my own over the years, projects that just quietly get canned, and of course they don't make the headlines. Probably the biggest cost is bugs in the field. Right? I mean, when air traffic control is closed for an afternoon because the computers have gone down, what's the economic impact of that? It's going to be huge. So, in conclusion, bugs really suck. Well, you probably knew this, maybe not quite how much. But not necessarily. I mean, that's a very black and white way of looking at the world, and as always, things are a little bit more nuanced. Actually, really to make bug-free software is incredibly expensive. And if it's the software that controls, the flight control software of the airliner that I'm on, I'm happy with that price to be paid for bug-free software. But if it's some piece of software that I'm buying and using for, creating a video or something, I'd rather it be a tenth of the price and crash occasionally than pay the fallback and have it completely correct. So correctness is just one of many competing concerns. And to make that completely bug-free software, I mean, every change. If you look at, I've got a friend who works and does flight control software, and every change goes through like 3 or 4 review panels to make sure that it really is absolutely fine. It's a very, very slow way of working. You need it in that case, and then you've got a spectrum of how important bugs are and how much you want to spend to make that software bug-free. So there's an optimal amount of bugginess for any software project. Bugs aren't always bad as well. You can read these despite the pixelation. This is XKCD. Right, so it's not quite the point I'm making, but there is a point. Sometimes bugs are good. So the best thing you can do is, clearly prevention is better than cure. Right? So here's a quote from if Maurice Wilkes was the first programmer, then Brian Kernighan can sort of be described as one of the real fathers of modern computer science. Invented Unix and C, among other things. And he has this nice quote, right? Debugging is twice as hard as writing code in the first place, so if you write the code as cleverly as possible, you are, by definition, not smart enough to debug it. Or, to put it another way, from Oscar Wilde, I'm so clever that sometimes I don't understand a single word of what I'm saying. So the point is, if you write the code, if you really push the limits, you're going to end up with buggy software. And we're not generally, most of us, quite as smart as we think we are. Another way of putting this, I remember reading this years ago. I read it just, it was a posting on a news group, and I read it just pertinent time in my career, I suppose. And I tried to find the guy who originally wrote this, so I could properly attribute it, but my Google foo let me down. So it's very much like riding a motorbike, learning to ride a motorbike. When young, particularly bad problem with men. Young man learns to ride a motorbike, right? Starts off kind of wobbly, right? Very slow, but he's at the limits of his ability. And he's going slow because his abilities don't let him ride that bike very fast. And as he gets better, and his abilities grow, then very often that young man will just stay at the limit of his abilities. And within a couple of years, he's zooming all around the place at 100 miles an hour. If he's lucky enough to survive into middle age and continues riding his motorbike, he'll probably learn the lesson. Maybe he sees a couple of friends die, maybe he just gets a little bit more sensible. And if you see a middle-aged biker, they'll be riding the bike nice and slowly, nice and comfortably, well within the limits of their abilities. And software developers are just the same, right? You see a lot of code written by somebody, fairly new. They're not a rookie programmer anymore. They kind of know what they're doing, but then maybe, often you see this in people at early 20s. They write the code, they write some really clever stuff, really cool. You can just change this bit and everything changes. I don't need to, my code is ultimately flexible or really fast. And yeah, more often than not, either it doesn't work there and then, or it's so subtle that you try and change anything and everything falls apart. Another way of saying this is a slightly different angle, but more haste, less speed. So I don't know if anybody knows this, but I'd recommend everybody read this book. It's a brilliant book. There's lots of really interesting things. This guy's it's a psychology text, but it's not kind of wishy-washy psychology text. It all talks about real experiments. This guy's in economics Nobel laureate, and he does it in behavioral economics. Anyway, one of the pertinent things in here is what they call planning fallacy. And they looked at the psychology of why things take so much longer than we think they're going to do. And it didn't actually talk about software at all. I think their case study was the Hollywood in Scotland. But just sort of plan things out at the beginning. And you think, yeah, we can get this done in 6 months or a year. And people just naturally, they can't help it. They just tend to be so optimistic. And they don't account not only for things being more difficult than they expected, but someone on the team will get divorced, someone will leave for another company or whatever, and these external things will screw up as well. And not leaving enough time in the project is a very big source of bugs. Not because you don't have time to get the bugs out, but because you're forced to take shortcuts, and you're forced to do things in that more haste, less speed style. So if you give yourself in the planning phases enough time, then you can do a lot better on prevention, and actually you can end up getting out the end quicker. Right? By giving yourself not enough time can often mean the project takes longer than it would if you'd done it properly in the first place. Lots of other good practices you can do to prevent bugs. Assertions, defensive programming, code review, testing, code coverage. We all know this stuff. It's kind of shocking about how little of it actually happens. Right? I mean, code coverage is a great example. I've done this before, we'll see if it will. Take a risk and see if it's well. Right. So raise your hand if you've ever done code coverage on a project. Okay. And then keep it raised if you're really surprised by the results. And keep it raised if you found those bits that those bits that weren't covered really had bugs in them. And keep your hand raised if you do code coverage as a matter of course. All the hands go down. Last time I did that, there were more hands up for longer, but the effect happens. We don't do that good practice stuff, and it's kind of it's a real shame. I don't know why, and we should as a community we should do more of it. And there are tools that we can use. I'm going to talk a bit about tools in a minute in more detail. So these are generally tools that help you prevent the bugs or find the bugs that you didn't, before anybody else even found them, before the customer reports them, before the test team even finds them. But whatever we do, there will always be bugs. Right? So we need better tools to help us find and fix those bugs, and that's why we started UndoSoftware. We felt that we could do better. So I'm going to try and do a couple of demos, which is always a dangerous thing to do, but demos speak was worth 1,000 words or whatever. So Undo is a reversible debugger. It runs on Linux, but hopefully this will be interesting even if you don't use Linux. I'm going to show demos today in Eclipse. You don't have to use Eclipse. It's a replacement or a wrapper for GDB, so you can use Undo anywhere that you would use GDB. But Eclipse kind of makes the better demos, so we'll show it in here. So here's a program, a fairly simple little program, and let's run it. Here we are, it's just compiled up, now it's stopped at the start of main. And I've got my 3 local variables. They're all uninitialized. B and C is 0 just by fluke, right? That's what happens in C. And I can single step forwards and gone executed one line of code, and A has become initialized. Right? This is all really standard debugger stuff. Debuggers have done this for years and years and years. They let you step twice. And I can see the data change as I step forwards, which is great, really useful for finding out what your program is doing. What we really want is to be able to go backwards. So if I click this back button, we go back a line. And now note that C has gone back to its uninitialized state. So I can go back again, I can go back again. Right? And I can go back and forth to my heart's content. And note that we're not just following the program counter, we are unwinding the global state of the program. So this is really useful because what debugging is all about answering that how did that happen question, how did I get here? And debuggers generally, most debuggers only let you go forwards. It's really answering the wrong question. Let's show something a little bit more meaningful. So this program here, it's kind of a dumb program, but I wanted to get a program that was complicated enough to have a real non-obvious bug, but simple enough to show in a demo like this. So what this program does is cache previously calculated square roots into a cache. And you would never do that in reality. Square roots are very cheap to calculate with modern hardware, but we can pretend it's doing some other operation, maybe it's looking up a database or something like that. And so our cache here is very simple. It's an array of structs, and we just map values onto their associated square roots. And the function we care about today is cache calculate, and given a value, it will return the square root by first looking in the cache. Right. really, really dumb, linear search, no fancy binary chops or tree structures or whatever. We just linearly search through the array, try to find an entry in that cache where the value matches, and if it does, return the square root. And if it doesn't, calculate the square root, store it in the cache, and store a couple of adjacent values on the assumption there's some kind of locality of reference. And here's my main function, which really doesn't do anything other than test, and just gets a random value, passes it into cache calculate, and asserts that what's returned really is the square root. If you've already spotted the bug, please don't shout out, because you'll ruin my demo. Right. So we run this in the debugger. Again, just compile up, here it is, stop to main, off we go. Okay, so bang, it's blown up, as we were probably expecting. An assertion has fired. Note that I'm deep inside C library here, right? This is not just debugging C source level code, this will debug machine code, it just works on arbitrary processes. And I can look up the call stack, I can go back into my own code, and I can see, yeah, okay, this is the assertion that failed. And this is as close as most debuggers get to telling you how did I get here, what happened. It's kind of a guess, right? The debugger looks at the stack and guesses where you've been, and that can be very useful for a lot of simpler bugs. But bugs like in this case, the bug itself is not directly on the call stack. None of these functions that we're looking at here contain the bug. So rather than just popping up the call stack, let's click this uncall button. So this is like popping up the call stack, but it's really rewinding the program. All our globals, everything else are going back. Go back, and we go back. So now we can start to debug this in our own code. So what's happened? So square root is not equal to check. Value, I can look up here, I can see value is 255. So I've passed in 255 to my cache calculate function, and it has returned 0. 0 is not the square root of 255. So the question is, why did that happen? Well, let's go and have a look. So we go back in time. And now I'm going to do this. This is reverse step into, so this will step into the cache calculate function so we can see what it returned, why. So here we are. So it's returning, so it's hit the cache, it's returned something from the cache. I is 90 here, right? So it's returned the 90th element of the cache. So at this point I'm going to have to try and type one-handed. I need a Madonna style head mic. Right, so let's have a look. And sure enough, the 90th element in my cache contains garbage. So this is a difficult bug to debug because someone has corrupted my data structure at some point in the past, and I've got no idea when. I've really got at this point, with the traditional debugger, I've got two options open to me. I can just stare at this code until I can see the problem, which in this case is okay because it's only a few lines long, but in real programs it doesn't really help. Or I have to run it again and add more assertions, and I have to do that repeated trial and error thing to try and find out, well, what happened earlier. But here, we can just, it says a watch point. Right? Watch point, sometimes referred to as a data breakpoint, exists in most debuggers. Set the watch point, you run forwards, the debugger will stop when the data changes. But of course I'm going to run backwards. When I run backwards, this will go back in time to the last point that value in the cache changed. So that will take me back to the line of code that last updated this line of cache, which is probably the line or close to the line that is responsible. So here we go. So we've gone back in time, and we can see here that the 90th element of the cache contains good data. The square root of 40 is 6-ish, integers. And I can actually do, this is kind of match of the day style action replay here, right? So I can step forwards, and we can see, there it is, okay. So there's my data structure being corrupted. So I've gone straight back into time, straight back in time to the piece of code that I care about. Let's go back again, just before things went bad, to see what's going on. Okay, so we're writing value 2 and square root into the associated members of the cache entry, where value 2 is this value and square root is its square root, and value 2 is -1. So I've tried to take the square root of -1, which is never a good idea unless you have imaginary numbers. So Next question becomes, well, how did that happen? And okay, pretty easy at this point to do this by code inspection, but this is a demo, so let's sort of follow this through. So I'm going to add another watch point into value 2. And I'm going to run back. Okay, it's initialized here. So I can single step. I can see, okay, so that's where it's initializing. So it's initializing at the head of my, top of my for loop. And the problem is, you'll notice that value is 0. So remember I said we cache adjacent entries of the square roots. So trying to work out the square root of 0 is fine, and it tries to get 1, which is also fine, but it also tries to get -1, which is not so fine. I can go to the call site, and we can just see another action replay of that. If I go, we can just see exactly what's happened. So if I, the value and square root of the entries in the cache, and these are the local variables that we're doing here. And so if I do a step over that function call, we can see it returned the right thing. Right? I asked it for the square root of 0, it returned 0. That's fine, but as a side effect, it left my cache in a bad state. That's an example of a kind of bug where the bug itself happens quite fast. And this is one of the vectors that makes bugs difficult, and this is one of the places you really want the debugger to be able to go back in time and tell you what happened and be able to stitch together that piece of time. So another demo, but I'll go back to actually just realised I skipped ahead of myself. But so look, the process of debugging, right? The archetypal needle in a haystack. You have often millions of lines of code, certainly many thousands of lines of code. Your machine is executing billions of instructions every second, and you're often looking for that one bad instruction. Right? So you're a needle in a haystack. Sometimes it's easier, right? Sometimes the bug's pretty glaring, and we can find it without too much difficulty. Sometimes it's what our friends in the military would call a target-rich environment. So what are you going to do? Stop, get away from the computer, go for a walk. Right? I mean, I expect most people have this experience. You're banging your head against the brick wall all day long, getting really frustrated. You give up finally, maybe it's late, and you leave, and before you've even left the building, maybe you realise, get away from it, go for a walk. You rubber duck debugging, and if anyone has heard of this, this goes back to, some people, so let's go back to, I think it was a professor at one of the US universities who got sick of students asking questions in the lab, and I think everyone will have had this experience. You've done any coding in a team, you go up to somebody and you say, I'm really stuck on this. I've been banging my head against a brick wall. I think it must be a compiler bug or something. This is just impossible. Let me explain. Maybe Frank, you can help me if I explain what has happened. And you begin to explain the situation, and you go, actually, no, I know what it is. So the professor would say, right, before you ask me why your program doesn't work, you have to go and talk to the rubber duck in the classroom inside and explain the problem to the rubber duck. And if he can't help you, then you can come to me. Now, unless you work somewhere particularly kooky, you might not feel comfortable talking to a rubber duck. But you can, I find personally, write it down, just write the description. I find it works better if I'm writing on paper than if I'm typing. I think it's related to that table talk thing. If you write a description of the problem and why what you're seeing is completely impossible, sometimes it becomes clear. Printf is a fine debugging tool, much maligned, but sometimes it does what you need. But it's all of printf and these other tools are all about that trial and error, repeated runs. So I did my demo in the wrong order, but you get the idea of what I was thinking with the flow. So what you really need is reversible debugging. Well, not what you really need, a tool when it all goes wrong, if you like. So reversible debuggers, as we saw, let you step backwards as well as forwards. And I mean, can't claim to have been the person who thought of this or the company that thought of this idea. It's not a new idea. In fact, there are papers on this going back to the 1970s. And there's been, it's actually not that big a leap of imagination to use a regular debugger and think, you know what, I really want to go backwards here. What we are the first people to do is to make this work in a way that is genuine reversible debugging, so you've got full data visibility, and you've got the ability to record real-world, very complex programs, and you've got the ability to do it in a performance that you need. So just to do the trick, if you think about why this is difficult, right? When a computer program writes the value to memory, whatever was there before is gone forever, unless you do something to be able to reconstruct it. Same for the register. So the naive way to implement this is every instruction, you record the delta. You record what was there before, and you store it in a log, and then if you want to go back in time, you can look in the log and see what used to be there, and you can reconstruct your state. But it's extremely slow, and it goes, and it generates huge amounts of log, right? Issuing billions of instructions every second. Even if you just store the delta for each instruction, you're still generating gigabytes a second. So we do it a different way. I'll get onto that in a moment. That means that we get the performance and the completeness that it can be used. So we use, customers include the scientific guys at NASA and Lawrence Livermore, and they're doing, climate modeling and nuclear simulations and these kind of things, big jobs that run for hours and hours and hours on huge sort of supercomputers. And increasingly now in the enterprise, so it might be banking, it might be EDA tools, right? So the firms like Cadence, who they make the software that lets you just define your chip in Verilog, and you put the source code in, and then out comes the design for your chip that you can then go and fab. Huge pieces of code, and they use it all the time. Love that before I skip ahead. So here's a quote from a happy customer down the bottom. It says, "I've already been able to fix a deadlock that was driving me crazy for a week in only 10 minutes." And that's kind of, I like that quote because it just snappily says that's what we do, that's the value. Here's a slightly longer quote from another happy customer. So this is Cadence, as I just mentioned. Yeah, they have hugely complex software, right? Modern microchips, billions of transistors. They have these simulations that run for hours and hours and hours, and they're extremely difficult to debug. Because what they do, actually, they take the Verilog, they're kind of a compiler. The simulators take the Verilog or the VHDL, and they generate x86 code that is functionally equivalent, and you can run your simulations much more quickly than if it did an interpreted thing. It still runs with slowdown of usually hundreds of thousands of times at least, but at least it runs in reasonable time. And these things run for hours and hours. And they had a bug. This particular quote is referring to a bug they had where it was failing at a customer site when they were running simulation, and it happened like 1 in 100 times, and they had no idea. And they had that. It's that like I showed the demo. It's a -1 in memory that we shouldn't have been there. And so they took this. They actually ran about 30 copies. They've got a big compute farm. They were running 30 copies simultaneously in undo, so they could capture it. Because it takes all day and fails 1 in 100. Finally captured it, and then they were able to get straight to the root cause of the bug. That's bizarre. Okay, right. So here's another quote from Brian Kernighan, Rob Pike as well this time, the inventors of C and Unix. They have a book called The Practice of Programming, and it's about taking computer science graduates and turning their theory into practice so they can become professionals. And they have dedicate a lot to debugging, as one would hope, and they describe debugging like this. They say, reason back from the state of the crashed program to determine what could have caused this. Debugging involves backwards reasoning, like solving murder mysteries. I like this quote for a couple of reasons. One is it's back and backwards 3 times. That's lovely. But also I like this metaphor with solving murder mysteries for a couple of reasons. Well, mainly because solving murder mysteries is often portrayed in the media as some kind of like Sherlock Holmes or CSI, brilliant deduction, some genius mind, or perhaps some amazing technology. But the reality of a lot of crime scene investigation is just grunt work, right? Going through the phone book, going door to door, and just like debugging trial and error again and again and again. You can easily spend all week going again and again. So what you want is CCTV for your code. You want to be able to record what happened so that you can go back and see what happened. So we don't, sometimes say that the company actually is very badly named. We don't undo anything. Like we don't make the murder victim come back to life, but we let you see what happened. So on performance, as I mentioned earlier on, so how do we do this, right? How do we get it for, well, let's do the benchmarks first, let's do that of order. So this is comparing us to GDB, the open source debugger, which has a feature called process record. It's had it for a while now, and it does this recording in the way that you would expect. It records every instruction as it runs. And this is the time to run gzip, right? So this is zipping up a 16 meg file, and you run it natively, it takes you a second and a half. You run it in undo, yeah, okay, it slows it down, right? We're recording stuff, so it slows it down a bit, you know, it runs about half speed. You run a GDB process record, it takes you the thick end of the day, right? Slow down 50,000 times. And a similar story with memory consumption, right? You're generating huge amounts of log just to do simple things. And how do we get the performance that we get? Well, we do a snapshot and replay technique. So that is based on the observation that computers are fundamentally deterministic beasts. Right? If you run a program multiple times, and each time you give it the same starting state, and you feed the same set of inputs, then every time you run it, it will do exactly the same thing. This is why random numbers are difficult to generate. So, if you've been running for 1 million instructions, let's say, and you want to go back an instruction, well, if we've saved the starting state, you can go back to the starting state, play that forward, count 999,999 instructions, and there you'll be. Effectively gone back one instruction, and you haven't had to record everything as you were going. There is a catch. I said if you feed in the same set of inputs. So it's critical that when you do that replay, you feed in the same set of inputs. And there are various sources of non-deterministic inputs. There's system calls, there's thread switches, there's asynchronous signals, there's reads from shared memory. Even, in fact, some processor instructions are non-deterministic. If you add two numbers together, that always gives you the same results. But if you read the timestamp counter on x86, it'll give you a different answer every time, by definition. In fact, Intel lets them few pop flags. Some instructions leave some flags in undefined states. So we have to capture all of those sources of non-determinism into the log. And that's why if you look at the memory consumption, we're zipping up a 16 meg file and the space required is 17.8 meg. So most of that space is the 16 meg of reads from the file system that we've slurped in. Because it might be when you replay, maybe the file doesn't exist anymore, or maybe you're talking over a socket. Right? So we just record those reads into the system log, into the event log. When we replay, we just reconstruct the effects based on what's in the event log. And that lets us get this performance and this memory consumption that otherwise you can't achieve. We don't just save the starting state, we actually periodically snapshot. So when you want to go back an instruction, you don't have to go back and run the whole thing again. If it was a 12-hour run, you don't have to wait 12 hours for your thing to go back. You've got a snapshot that hopefully wasn't very long ago, and we'll just pick that up. And it all happens behind the scenes, as you saw in the demo. So let's do another demo. I like demos. So we finished with that one. Let me just close that one down. And let's do a threaded program. So I'm not going through this in quite the same detail, but here's a multi-threaded program that just looks after linked lists. It doesn't do anything, right? It just has this linked list element, very simple, singly linked list with a next pointer and a value and a header for the list with a lock and things, and functions to initialize lists and lock and unlock lists and add elements to lists and remove them, etc., etc. And we create two lists in an array, so we could easily make this more, but let's just keep it two to make it easier to think about. What's I say? Here we are. Right. And we've got this function, this tester function, which loops around and chooses a list at random. Okay, takes one of the lists at random, and then does a random thing on that list, either adding an element to it or removing an element from it. Actually, that case never executes in this demo. And our main function just creates a couple of threads. Could easily make more threads, but we'll just again do two to make it easy to reason about, and calls the tester function on each thread. So we have two linked lists, and we have two threads, and each thread is doing a random operation on a random list. They're all locked, so it should be nice and safe from a concurrency point of view. And let's run it in the debugger. Okay, so here we are at the top. Oh, let me get rid of my old things because it doesn't like that. And let's get rid of those breakpoints as well. Okay, so here we are at the top of main. Off we go. And well, I don't we could wait here an awfully long time, so let's interrupt it, see what's happened. Okay, so I've got 3 threads, as I expected, right? My main thread and my 2 worker threads, but this thread seems to be stuck. Now, maybe I'm just being impatient, or maybe the bug is sort of at a higher level, so let's see if it returns from that function. No, not returning. So it's definitely stuck in this lock routine. Again, we're deep inside the threads library here, but that's okay. So let's go back into our own code so we can try and get a better idea of what's going on. And yeah, sure enough, here we are at this mutex lock. So that mutex lock is not returning. Something is, somebody or some line of code has locked that list and is not unlocking it. That's what that means, right? There's a deadlock. So what's responsible? Well, if I put a breakpoint here with a classical debugger, pointless thing to do. I know I'm not going to hit that breakpoint. I'm not able to go further forwards because I'm deadlocked. But if I go backwards now, I'll hit that breakpoint the last time that the lock was taken. Actually, that will hit the last time that any lock was taken. So if I just go here and Control C that, oh, that's Control C that list pointer, and set breakpoint properties, and let's make it a conditional breakpoint. All right, so now that breakpoint is only going to stop when that particular list is locked. So that, if I run backwards, that's going to show me the guilty party. Here we are. Okay, so we've gone back in time to the last time that list was locked. So let's see what happened. So now we run forwards, replaying history. And oh, we've got an escape. Right, so we locked the list here, and we've got a return escape with no unlock. So this is a classic resource leak, right? And it's also, I think, a good demo. Obviously, it's nice to show threads, but also shows you that this technology is not designed to find the bugs for you. You still have to be smart. You still have to use your skills as a developer, but it gives you the information that you need in a way that's much more convenient to get. So there's my couple of demos. I'm just going to wrap up. And now I'm going to wrap up, and then we can go to Q&A. I'm running slightly ahead of time, but that's okay. So, what have we seen? So it works on unmodified Linux x86. Actually, that should also say ARM. We now do ARM. So you don't have to compile any special compiler flags. You don't need to link against any special libraries. You don't need to run this in a VM. You don't need to have kernel patches. It just works. I talked before about one of the vectors that makes bugs difficult is if you have a long time between the bug itself and noticing its effect. That's one of the vectors. The other vector that makes bugs difficult is how deterministic is it? Right? Is it every time you run it, does it do something different? Maybe it only happens 1 in 100 times, maybe it fails every time, but in a different way each time. So the repeated trial and error thing really gets tricky. And but life gets really interesting when you have a combination of the two. And so this is where we have the greatest value with this kind of technology, because now you can get that deterministic replay, and you can go back in time, and you can sort of binary chop history if you want, and you can set your watch points. It's also, we didn't really expect this when we started. It's one of those sort of happy things you find when you do these sort of projects that turns out to be really useful for navigating your way around source code that you're not familiar with. And in modern software projects, you often have large teams. Maybe the guy who wrote the code's gone, left for someone else. Maybe maybe it's third-party library, you've got it from somewhere else or whatever. Maybe you're just new to the team. Being able to navigate around a large, complex web of code, and you often get these things like function pointers that make life really difficult to track through. Very useful. So really, what you have is a source code flow analysis tool designed for debugging, but because it will help you understand source code. And it does what you'd expect a debugger to do. It lets you attach to a running program. Obviously, if you're attached to a running program, you can't go back in time to before you've attached. And does watch points and breakpoints and all the kind of things you want your debugger to do. And critically, it fits seamlessly into your environment, so you don't have to bring a new IDE along. If you like to use Eclipse, if you like to use Emacs, if you like to use DDD, if you like to use the command line, you just do whatever you were doing before, and you can just use this. Actually, the product I've shown today is our direct sales product, so that does work with GDB. It's not really a debugger, it's a process record and replay engine, and then we have other debugger front ends that you can use. So ARM just this month launched the latest version of their DS5 tool suite, which contains a thing called Application Rewind, which is us underneath. And you can also get the Roadwave Total View Debugger, which has us underneath their reverse functionality as well. Questions? Yes?
Is there a reliance on Linux? You don't know the successful?
Right now it will only work on Linux. We are quite tightly coupled to the OS because we record all of the system calls and all those other interactions. We work at the OS system call ABI layer and the CPU architecture layer, which is a good place to be because they're very well defined. But it does mean portability is an issue. So we just ported to the ARM, and it was a huge project to get our JIT compiler and everything onto the ARM. We will go onto other platforms. Other Unix-like platforms are going to be easier for us, so probably going to come first, right? So that means Apple, that means BSD, and those kind of platforms. A bit embarrassed to say it, given where we are, but Microsoft is it's just a big leap. It's a completely different system. So we don't have any direct plans to get onto Microsoft. Any other questions? Yeah.
So you said that there has been a lot of research on this topic. From what you've done, it seems to me like it's the obvious right solution. Why haven't people done this before?
Well, one answer is I don't know. You'll have to ask everybody else.
I'm expecting that there's some kind of difficulty, like people have tried this and it doesn't work. So.
There have been a number of research papers, and some actually have followed a similar approach with the kind of replay approach. But the thing with research, I've done a fair bit of research myself, and you'd have a lower. It's research, not product, right? So you don't. And the idea is not that you make it complete and you make it work with the kind of performance you need and the completeness you need. So all of the implementations before, they wouldn't handle shared memory, they wouldn't handle IOPSLs and do unknown things and all these difficult things that real programs do. And so it's just a question of complexity. And in fact, it surprised us when we founded Undo. Actually, we founded back in 2005, and for a long time it was sort of an evenings and weekends project. We had other day jobs to feed ourselves, and it took a lot. It was a lot harder than we expected. And I say, I'm glad that I didn't know how hard it was going to be, because if I'd known, I would have started. So it's getting to that point. It's getting from toy to toy is unkind. From research vehicle, from proof of concept to I can really use this. So like that cadence case study I gave just before, right? People using this on codes that run for 12 hours and do really complex things. That's the hard bit. And happily for us, nobody else has done it. Yes?
Are there any pathological cases that you have to deal with?
There are certainly pathological cases. There are cases that work better than others, so we say. There's nothing that we really can't deal with. But it's fair to say that we kind of cheat with threads. So what we do, we are working on this, but right now, when you record, the threads are all serialized. So it's still a preemptive multi-threading system. So you can still get race conditions, like that we saw in the demo, but it's as if you're back in the old days when you had a single CPU core. So it'll only run on one core. So we're working on things to do better with multi-core and to get. That's a scalability thing. And it,
surely that would take your performance if you have
absolutely.
high performance
Yeah. So that in sort of paradoxically, the ideal, the perfect, the embarrassingly parallel problems turn out to be pathological for us. Fortunately, most problems are quite pathological when it comes to parallelism, and it's really hard to get those 24 cores all playing at the same time. Yeah.
Go back, change the value of variable.
No. That creates interesting paradoxes. But that's kind of a trite answer. No, it's something we don't support right now. We do get asked about it a lot, and I think we probably will do it at some point. But it is a tricky problem because of the particularly because of the replay approach that we have. Go back and pick up one of these replay snapshots and play it forwards. It doesn't have those. It doesn't have the same interaction with the outside world. So any file descriptors probably won't be open. So any file operation you do is probably going to return eBAF. And you know, in the general case, it's impossible because you can imagine a web server halfway through an exchange with a client, go back in time, change something, try and run forwards again. Do you want to replay those interactions, or do you want to hope that it would have done the same thing? So it's complicated. It's particularly complicated to explain what will work and what won't work. So at the moment, we just don't let you do that. We do let you change data in record mode. So when you're running and you're recording, you can change variables and then just save that into the log as a non-determined event and replay it. At the moment, we don't let you change history. So it's a CCTV camera, right? It shows you what happened, doesn't let you change what happened. Yeah.
You sort of school of thought that as you move to functional programming styles, that helps reduce the number of bugs. Mm-hmm. Is that something that you've actually thought in the real world, or is that more an academic?
I don't really feel qualified to answer that question. I mean, it certainly is true that some languages are more bug prone than others. So I mean, in my demos, I didn't show any pointer dereferencing bugs that are common in C, and obviously those bugs just don't exist in other languages. So I think this was the last question. But yeah, definitely the lower level language, the more difficult the bugs, the more likely the bugs are, the more difficult they are to get out, and that's one of the reasons why that's been our first focus. We might look at Java and other things in the future, but right now it's those languages that you need to get the performance, and there's a lot of C and C++ out there that are still, being written still. I think it just took over the top spot on the TiVo thing as the most popular language. But yeah, there are lots of solutions, and as I said at the beginning of the talk, prevention is better than cure. But we're just we're the doctors here when you do get sick. All right, I think we're out of time. Yeah, I'm going to be around, so come and grab me and ask any questions, and feel free to email us undo-software.com to really put it up.
4 minutes.
All right, thank you.